Hello everyone, welcome back to my channel. So in this video we are going to learn about the power and bandwidth calculations in WBFM signal. Okay, so little bit complex these topics, right? Try to understand one by one. If you are first time to my channel, please consider subscribing and encourage me to do more videos like this. So WBFM signal. So first we'll discuss about power. Okay, so the standard time domain equation of WBFM signal we have derived in the previous video. So if you have not seen that video, please see that video. I have derived very clearly how to derive this WBFM standard time domain equation. So we have got as AC into summation n is equal to minus infinity to infinity Jn of beta into cos 2 pi fc plus nfm into t. Okay, so this is the standard time domain equation which we have got. So now s of t, I'm expanding this. Okay, so I'm expanding this. So AC into, first I will substitute n is equal to 0. So n is equal to 0 if you substitute. So J naught of beta and substituting n is equal to 0. So this term will get cancelled. So what you left over is cos 2 pi fc into t. Okay, plus now I am substituting n is equal to 1. So when I substitute n is equal to 1, so AC into J1 of beta, just n is equal to 1 into cos 2 pi fc plus fm into t, because n is equal to 1. So fc plus 1 into fm is fm only, so fc plus fm into t, plus now I am substituting minus 1 because we have n values both negative and positive. So AC into, what can we write here is J minus 1 of beta, into cos 2 pi fc minus fm into t. Okay, plus I'm substituting n is equal to 2 now. So when you substitute n is equal to 2, what you'll get, AC into J2 of beta cos 2 pi into fc plus 2fm into t. Yes or no? So n is equal to 2 here. So similarly you'll get the coefficient J2 of beta. So that's what I have written here. Plus I am substituting n is equal to minus 2. AC into J minus 2 of beta cos 2 pi fc minus fm into, fc minus 2fm into t, plus so on. Okay, so this is the total time domain equation. So as I have told you, when you are calculating for power, because now we are discussing for power, so when you are calculating for power, we consider only amplitudes. So frequency is not a problem. So power only depends on amplitude. Okay, so when you have a AC signal, AC cos 2 pi fct, the signal like AC, so first of all we have to find the RMS value. So from the maximum, so this represents the maximum value. From the maximum value you have to find the RMS value, and we have to take the square of it to get the total power. Okay, so what I mean to say here is every term here is a cos signal. Okay, so this is one cos signal, this is another cos signal, and this is again a cos signal, and so on. Okay, so everything is a cos signal. So the amplitude here is, so if you want to calculate the power PT, so that is the total power of WBFM signal. Okay, so because this represents the time domain equation of WBFM, so power if you want to calculate of WBFM signal, so in the first term this represents the amplitude. Okay, so maximum amplitude. So first of all we are taking the RMS value and taking the square of it. Okay, so that becomes the power in this signal. Okay, so the power in this is completed. Plus, so power in this is given by AC into J1 of beta by root 2 RMS value and taking square of it, plus AC into J minus 1 of beta by root 2 whole square, plus AC J2 of beta by root 2 whole square plus AC j minus 2 of beta by root 2 whole square. Okay, plus so on. Okay, for 3, 4, 5 and so on up to infinity you'll get this. So what will get AC square by 2 j naught square of beta? Yes or no? So for this, AC square by 2 j naught square of beta plus AC square by 2 j 1 square of beta plus AC square by 2 j minus 1 square of beta plus AC square by 2 j 2 square of beta plus AC square by 2 j minus 2 square of beta plus so on. Okay, so if you take AC square by 2 common, so this becomes j naught square of beta plus j1 square of beta plus j minus 1 square of beta plus j2 square of beta plus j minus 2 whole square of beta plus so on. So what can we write this? The AC square by 2. So if you write in a summation form, we can write it as summation n is equal to minus infinity to infinity jn square of beta we can write. Yes or no? So from the third property which I have told you in the previous video, so when I'm telling you about the basics of Bessel function, so I have told you that summation n is equal to minus infinity to infinity jn square of beta value is equal to 1. Okay, so that means so the total power of WBFM signal is equal to AC square by 2. Okay, so that means the total power in the case of WBFM signal is equal to the unmodulated carrier power, so which is equal to AC square by 2. Since the power is same as the unmodulated carrier power, so since the power after modulation and before modulation, so after modulation the message signal is stored in carrier only. Okay, so the power after modulation, that is the modulated signal power, is equal to the unmodulated carrier power. That means what does this represents is amplitude of carrier is constant, because power depends on amplitude. Since before and after modulation power is same, we can say or we can prove that this. So this theoretically I have already told you in the first video of this angle modulation. So amplitude of the carrier becomes constant in the case of FM, and so this is how we can prove that practically. Okay, so amplitude of the carrier is going to be constant. So the total power in the case of WBFM signal is same as AC square by 2. Okay, so this you have to remember. Okay, right, we will now derive the equation for bandwidth. Okay, so in order to derive the equation for bandwidth, now we have to draw the spectrum of WBFM signal. So for that we'll again start with the standard time domain equation. S of t of WBFM signal is given by AC into summation n is equal to minus infinity to infinity jn of beta into cos 2 pi fc plus nfm into t. Okay, so this is the standard time domain equation of WBFM signal. So I'm expanding that. S of t of WBFM signal is given by now tell me, so AC into, first of all I'm substituting 0, so JC into j naught of beta into cos 2 pi fc into t, plus when I substitute 1, j1 of beta into cos 2 pi, same as the previous case, fc plus fm into t. When I substitute minus 1, AC j minus 1 of beta into cos 2 pi fc minus fm into t, plus when you substitute 2, j2 of beta into cos 2 pi fc plus 2fm into t, plus when I substitute minus 2, so AC into j minus 2 of beta into cos 2 pi fc minus 2 fm into t. So if I substitute 3, AC j3 of beta into cos 2 pi fc plus 3 fm into t plus AC j minus 3 of beta cos 2 pi fc minus 3 fm into t. Similarly, if I substitute 4, AC j4 of beta cos 2 pi fc plus 4 fm into t plus AC j minus 4 of beta cos 2 pi fc minus 4 fm into t plus so on. Okay, so we know that from the second property which I have told you for Bessel function, so j minus n of x is equal to minus 1 whole power n into j n of x. So for odd values n is odd, j minus n of x is equal to minus j n of x. Similarly, for n even, if n is even, j minus n of x is equal to j n of x. Okay, so we'll use this property now. So s of t of WBFM signal is given by, now see, so for the first one it is same, so AC into j naught of beta into cos 2 pi fc into t. Okay, plus now see, so what is the second term is also same, AC into j1 of beta into cos 2 pi fc plus fm into t. Now see the third term, in this we have j minus 1 of beta, and 1 is an odd number, so j minus 1 of beta, so j minus 1 of beta is equal to minus j1 of beta. Okay, so I am writing that, so it becomes, so this becomes minus j1 of beta. In the place of this j minus 1 of beta, we can write it as minus j1 of beta. So when minus multiplied with plus, so minus multiplied with plus, you will get minus, so minus AC j1 of beta into cos 2 pi fc minus fm into t. Okay, but for the next equation, AC into j2 of beta, for positive values no problem, cos 2 pi into fc plus fm into t. Right, so here j minus 2 of beta is there, but because n is equal to 2, which is an even number, so j minus 2 of beta is equal to j2 of beta. So we can write it as AC into j2 of beta into cos 2 pi fc minus, sorry, this is 2fm, fc minus 2fm into t. Okay, so this is fc plus 2fm, sorry, I have written wrong. And this third term, third is also same, AC into j3 of beta into, so positive same, cos 2 pi into fc plus 3fm into t. So this is j minus 3 of beta becomes minus j3 of beta, so it will become minus AC into j3 of beta into cos 2 pi fc minus 3fm into t plus so on. Okay, so this is the standard time domain equation by using the second property in order to write the bandwidth. Okay, so you just note down this equation. I'll take another slide and I'll draw the spectrum. So I don't write any equation again, so I'll directly draw the spectrum. So first of all, this is a carrier term. Okay, so this is carrier term and its coefficient is depending on j naught of beta. Okay, so its coefficient is AC into j naught of beta. So carrier term, so from this equation, so we have carrier term because cos 2 pi fct is a carrier term. Carrier amplitude depends on AC j naught of beta, so it depends on the Bessel function at n is equal to 0. Similarly, cos 2 pi fc plus fm, fc minus fm, so fc plus fm and fc minus fm are called as first order sidebands. first order sidebands, because we have infinite number of sidebands here. So for 2 we have 2 sidebands, for 3 we have 2 sidebands, that is upper and lower sideband, and there are n number of upper and lower, infinite number of upper and lower sidebands. So Fc plus Fm, Fc minus Fm, first order sideband. Similarly Fc plus 2Fm and Fc minus 2Fm are called as second order sidebands, okay, and so on. Okay, so the carrier amplitude depends on J0 of beta, just remember this term. Okay, so I will draw now the spectrum of this wideband FM signal based on this equation only. Okay, so just see that, and if you want to copy the equation, then I'll draw the spectrum in the next slide. Okay, so now we'll draw the spectrum of this. So based on the equation which we have obtained, so I'm drawing the spectrum here. So I'm taking only positive frequencies. Note that I'm taking only positive frequencies. Okay, that means the negative half I'm not drawing, only one half I'm drawing here because it is sufficient for us for the analysis. So this is Fc. Okay, this is Fc. So its amplitude is AC J0 of beta. So as I have told you, so the amplitude depends on AC J0 of beta into cos 2 pi FCT is the carrier term. So when you draw the spectrum for this, the magnitude becomes half. So this becomes AC J0 of beta by 2. So I'm drawing only for positive frequencies. I'm drawing only for Fc. Minus Fc is negative frequency. I'm not considering. Okay, which is not required for us. Right, what is the second term which we have? AC into J1 of beta into cos 2 pi Fc plus Fm into T. Okay, so at Fc plus Fm we have an impulse function whose amplitude is AC into J1 of beta divided by 2. What is the third one? So minus AC J1 of beta into cos 2 pi Fc minus Fm into T. Yes or no? So this is the third term. So that means there will be an impulse function with negative amplitude, minus AC J1 of beta divided by 2, because amplitude becomes half. Similarly, fourth term is AC J2 of beta into cos 2 pi Fc plus 2Fm into T. Okay, so Fc plus 2Fm into T, so we'll write like this: AC into J2 of beta divided by 2. And similarly, fourth term is also, next term is AC into J2 of beta only, because J minus 2 of beta is equal to J2 of beta only. Cos 2 pi, the frequency changes here, Fc minus 2Fm into T. So there will be an impulse function at, this is at Fc minus Fm, this is at Fc minus 2Fm. Okay, similarly next is Fc plus 3Fm. This is Fc plus 2Fm. This is Fc plus 3Fm. Its amplitude is AC J3 of beta divided by 2, and so on. Okay, so here again it will be negative. So next term is minus AC. So J minus 3 of beta is equal to minus J3 of beta. So we'll get a negative impulse at Fc minus 3Fm. So this will be minus AC J3 of beta divided by 2, and so on. Okay, so this will be the spectrum. So if you observe here, why I have drawn decreasing impulse functions. So the concept here is the first property. So third property of Bessel function, which I have told you, I have used in finding the power. And second property we have used in the previous slide in order to write the standard time domain equation for drawing this spectrum. And now in order to draw the spectrum, I am using the first property. What is that property? As n value increases, Jn of beta value decreases. As n value increases, Jn of beta value decreases. So n value is increasing here. So 0 here, 1 here, 2 here, 3 here. So n value is increasing. So Jn of beta value decreases. So I have showed that decrease in amplitudes also. Okay, so that is why the impulse amplitude decreases when n value increases, so it decreases like this. Okay, so that is the reason. Right now this is the spectrum. So we are going to derive some important conclusions, or important points you can say, or important conclusions, whatever it is. So we have to write some important points here from the spectrum. So first point is, spectrum consists of carrier and infinite number of upper and lower sidebands. Okay, so spectrum consists of this carrier term Fc and infinite number of upper sidebands and infinite number of lower sidebands also. Okay, so spectrum consists of a carrier term, this one, and an infinite number of upper and lower sidebands. So when there are infinite number of upper and lower sidebands, ideal bandwidth, very important point here. So ideal bandwidth of WBFM signal is infinite, because there are infinite number of sidebands, so the bandwidth is also infinite. So ideal bandwidth is infinite. Second point is this one, as n value increases, Jn of beta value increases, Jn of beta value decreases. So higher order spectral components, that means higher order frequencies as n value increases. So higher order spectral components has lesser amplitudes. Okay, because n value increases, Jn of beta value decreases, so it will have higher order spectral components have lesser amplitudes and constitutes less power. Okay, so the power present in that is very less, because amplitudes are decreasing as n value increasing. So as n value increasing, Jn of beta value decreasing, so higher frequencies will have lesser amplitudes. Okay, so higher frequencies have lesser amplitudes, therefore due to lesser amplitude they will have less power. Okay, so that is the thing here. That is the second inference which we have got from this spectrum only. So by seeing the amplitudes only, we can say that as n value increases, amplitude decreases, and hence higher order spectral components have lesser amplitudes and constitutes less power. And the last point which you have to remember is, for some values of beta, J0 of beta is equal to 0. Okay, so what are those values are? Beta is equal to 2.4, 5.5, 8.6, 11.8 and so on. Okay, so for these values of beta, J0 of beta is equal to 0. So when J0 of beta is equal to 0, what will happen? AC into J0 of beta is also equal to 0. When AC into J0 of beta is equal to 0, so this component, this only carrier component Fc, so Fc, that is carrier component, so Fc, that is carrier component, vanishes, so it becomes 0. It will not be present. Okay, so it will not be present in the spectrum. So when there is no carrier alone component, then what will be there? It will consist of only sidebands. Okay, so it will consist of only sidebands. When you consist of only sidebands and you are transmitting only sidebands, then efficiency is going to be, modulation efficiency is going to be 100%. Okay, so for some values of beta, that is for these values of beta, so at least 4 you have to remember. These 4 you have to remember, because it is asked once in previous gate question, so you have to remember these values. Okay, So if possible, I will do that question also in the future. So J naught of beta is equal to 0. When J naught of beta is equal to 0, then carrier component vanishes and efficiency becomes 100%. So for these values of beta, efficiency of WBFM is going to be 100%. And for all the remaining values, FC is present, so efficiency is not 100%. Okay, so this is what the three inferences which you have got from the spectrum of this WBFM signal. Okay, so we have seen in the previous slide that ideal bandwidth of WBFM signal is infinite. So ideal bandwidth of WBFM signal is infinite. But when bandwidth is equal to infinity, what will happen is we can't transmit this signal. Even if you transmit the signal, then multiplexing becomes very difficult. Multiplexing becomes difficult. So what is multiplexing? I'll explain you in the next slide or next video, so don't worry about this. So multiplexing becomes difficult. So bandwidth of the signal, so for efficient multiplexing, bandwidth of signal must be as low as possible. Okay, so multiplexing means transmitting the two or more signals through the same channel. Okay, so just as our cable TV wire. So in the cable TV wire, in a single wire, we are transmitting all the signals, all the video signals. Okay, single channel, we are transmitting all the video signals of different TV channels. Okay, so that is called as multiplexing. So that multiplexing will not be possible if bandwidth is going to be very high. Okay, so if the bandwidth is more for signals, then we cannot transmit more signals through the same channel. Okay, so that is the difficulty if you have the bandwidth high. Okay, so ideal bandwidth is going to be infinite. This is the important point which you have to remember, as I have told you already. So in order to have the practical bandwidth, so this is ideal bandwidth. So practical bandwidth, so a scientist by name Carson has given Carson's rule for finding the bandwidth, transmission bandwidth. So Carson's rule for transmission bandwidth in the case of WBFM signals. So according to Carson, what he have found is beta plus 1 number of upper and lower sidebands, along with carrier. Okay, so beta plus 1 number of upper and lower sidebands along with the carrier has significant amplitudes, and constitute 99% of total power. Okay, so he has given this statement. So beta plus 1 number of upper and lower sidebands along with the carrier has significant amplitudes and constitute 99% of the total power. Okay, so what does it mean? So this means that suppose if you take beta value is equal to 2. Okay, so beta plus 1 means 3. So 3 upper sidebands and 3 lower sidebands. 3 upper sidebands and 3 lower sidebands means, so first one is carrier, which is FC. Okay, so FC and 3 upper side bands. Okay, 3 upper side bands. This is FC plus FM, this is FC plus 2 FM, and this is FC plus 3 FM. 3 upper side bands and 3 lower side bands. So this is FC minus 3 FM. Okay, so these are the frequencies, positive frequencies. So in that case, what will be bandwidth? So bandwidth is equal to FC plus 3 FM minus FC minus 3 FM. So it will become 6 FM. Yes or no? So it becomes 6 FM. So why this total concept come into existence is again from the spectrum. So as in the spectrum, as I have explained you, as n value increases, Jn of beta value decreases. Jn of beta value decreases. So as Jn of beta value decreasing, so we can eliminate some of the higher order spectral components. Higher order spectral components. Why we can eliminate? Because they have insignificant amplitudes. When they have insignificant amplitudes, then power is almost equal to 0. So power is not present in those amplitudes. So we can eliminate those we can eliminate those higher order spectral components. Then how many spectral components have to be removed or eliminated is given by this Carson's rule. So he states that you have to consider beta plus 1 number of upper and lower side bands. Okay, so in order to eliminate that only, so he has given one rule, beta plus 1 number of upper and lower side bands along with the carrier, and they constitute 99% of the total power. Understood? So this is what the Carson's rule importance is, and it is again from the spectrum only. So this is 6 FM. So bandwidth which we have got is 6 FM. So this is for beta is equal to 2. Okay, so when beta is equal to 2. So generalizing this concept, so beta bandwidth we can give it as 2 into beta plus 1 into FM. Okay, so in this case, what is beta? Beta value is 2. So bandwidth is equal to 2 into beta plus 1 is 3 into FM, which is equal to 6 FM, which is obtained like this. Okay, so this is for FM, beta is equal to 2, and general for any value of beta, the bandwidth in the case of WBFM signal. So bandwidth in the case of WBFM signal is 2 into beta plus 1 into FM. And what is beta again? So beta is equal to delta F by FM. So beta plus 1 can be written as delta F by FM plus 1. So which is delta F plus FM by FM. Okay. So bandwidth other formula is 2 into beta plus 1 can be written as delta F plus FM. Okay, this FM and this FM. So this FM and this FM will get cancelled out. So final answer will be this. 2 into delta F plus FM. Okay, so this is the formula for bandwidth. Okay, so this formula is called as Carson's rule. This bandwidth formula is called as Carson's. This bandwidth formula is obtained from the Carson's rule, and Carson's rule states that beta plus 1 number of upper and lower side bands along with the carrier will have significant amplitudes and constitute 99% of the total power. Okay, so this is how we can calculate the power and bandwidth of WBFM signal, both ideally and practically. Okay, so I will just tabulate the formulas for power and bandwidth, because these are very important when you are solving numerical problems on frequency modulation techniques. So for narrowband FM and for wideband FM. So for narrowband FM, the total power is PC into 1 plus beta square by 2. Sorry, so PT into 1 plus beta square by 2. And for WBFM, the total power is equal to PC, which is equal to AC square by 2. Okay, so for bandwidth in NBFM, so bandwidth is equal to twice the message signal bandwidth, and bandwidth in the case of WBFM is bandwidth is equal to 2 into beta plus 1 into FM, or 2 into delta F plus FM. Okay, so these are the most important points which you have to remember in the case of NBFM and in the case of WBFM if you want to solve the numericals based on frequency modulation. Okay.